Hello everyone, I'm Shaiting Li from Zhejiang University. It's a great honor today to present our work, SSVQ Unleashing the Potential of Vector Quantization with Science Bulletin. This work was done during an internship at Vivo Mobile and has been accepted by the International Conference on Computer Vision 2025. Also, our code is publicly available. Vector quantization is a hardware-friendly quantization algorithm. Due to its significantly lower quantization error compared to uniform quantization, it holds great potential for ultra-low bit compression scenarios. As shown in this fig, here is a basic VQ pipeline. Given an unpressed weight, it is first shaped into a 2D matrix. A clustering algorithm then generates standards and indexes. Only the codebook and indexes are saved instead of the weight itself. The compressed weight can be restructured via lookup table operations before being shaped back to its original dimensions. Fine-tuning is always essential for extremely low-bit quantization. Although vector quantization has significantly smaller quantization errors compared to uniform quantization, its potential during fine-tuning is limited. In vector quantization, to maintain the compressed format, only the codebook can be fine-tuned rather than the weights themselves. This means that all weights vectors close to the same code word can only be updated in the same direction, greatly limiting the fine-tuning potential. Consequently, many big top vectors are updated toward the suboptimal values, which ultimately downgrades the model accuracy. So how can we boost vector quantization during fine-tuning? To fully harness the potential of vector quantization during fine-tuning, we introduced a novel VQ paradigm called science-splitting vector quantization, which empowers each quantized weight to update independently in alignment with its gradient direction. Our approach begins by extracting the sign bit of the weight as a 1-bit mask and clustering the absolute values of the weight. The inherent properties of clustering effectively offset the 1-bit storage overhead introduced by the sign representation, because we only need fewer standards for all positive weights to cluster. Next, we introduce implicit variables to learn the sign bit, and the gradient is approximated by straight-through estimator. So our SSVQ enables the compressed weight to update in a different direction with the code word, which greatly enhances the representation ability. One challenge is that the sign learning could be unstable because when a sign flips, the value of the quantized weight changes by twice of the magnitude of the code word. When either is suboptimal, the sign bit could oscillate between those two values. To overcome this, we interactively freeze those signs which jumps frequently. Extensive experiments on various models and tasks, including classification, detection, segmentation, image generation, and popular LLMs, demonstrate that SSVQ achieves a significantly superior compression accuracy trade-off compared to conventional vector quantization and uniform quantization methods. Furthermore, we developed a hardware simulator to validate the gain of the inference speed. The key design is our weight coding module between the main memory and the weight buffer. Mask values determine the weight reconstruction process. Positions with mask equal to 0 are computed as the two's complement negatives, while mask equals to 1 preserves original values. The reconstructed weights are then stored in the weight buffer. On the DEIT tiny model, our SSVQ achieves a 3 times speed up over the 8-bit compressed model by reducing the memory access. To summary, in this work, we first introduced a novel vector quantization paradigm, science-splitting vector quantization, to boost accuracy gains during fine-tuning. And we then proposed an enhanced freezing strategy to ensure the stability during training. And furthermore, we built a cycle-accurate hardware simulator to validate the speed-up gain of our algorithm. If you have any further questions or if you're interested in quantization, feel free to contact me by email. And again, our code is available. Thank you for listening.